Hello, everybody. Welcome to this lecture of computer system security. Today, we're gonna finish our lecture number 2, which is cyber attacks. And if you remember, we've talked about different payloads or malicious activities that we may see for over different malwares. And we've talked about staying hidden for some malwares, which makes sense. For example, if the developer, the attack developer has found some type of backdoor in the program, so he or she would like to use that backdoor, and of course he or she doesn't like to show any sign or any behavior that reflects that he's here or she's here, and there are some malwares running on background. So he or she, the attack developers, kind of prefers to stay hidden. So we've talked about this. And we talked about backdoors, what are the backdoors, and stealthing backdoors, which are a type of backdoors that are being used, the backdoor which are being used by attacker in order to compromise one of or maybe a couple of our security pillars. Now, there is another type of payload that I would like to talk about. And in this one, again, the developer prefers to stay hidden. So it means that the malware, it doesn't show any explicit sign of presence, and the developer tries to stay hidden. The reason is, again, he or she has found some backdoor, but there is a little difference here. We call them rootkits, a stealthing rootkit. And before that, I'm gonna first define what is a rootkit, and then we come back and talk about stealthing rootkit. A rootkit, or kind of a root privilege, is a program or application or process which has access to all components of our computer. We call it sometimes administrator access or root access, and it has this type of access, this level of access would have access to all privileges that we have in a computer system. That includes creating a file, defining a new file, opening files, sending information to input output, monitoring processes, for example, switching the CPU between the different processes. If you remember, we've talked about operating systems in the time sharing or multi-programming, for example. And we said that in time sharing, we will have multiple processes, and the CPU is here, and the operating system is supposed to assign the CPU to each of these processes. For example, this is process 1, process 2, and process 3. And the operating system is supposed to assign the CPU to each of these processes at a time. Process 2 takes the CPU, let's say for example, 100 microsecond. And then this is the operating system's responsibility to take it back and give it to process number 3. And now process number 3 goes and takes the CPU for 100 microsecond or whatever this time window is. But anyway, this kind of this action that we call the transition or context switch between different processes, it is a very kind of low level and high privilege operation that only operating system is supposed to be able to do that. But when you get the root access, the application that has the root access might be able to even call system calls or invoke the system calls that they do the context switching. So it sends receive network traffic, and all low level and kind of very important services that might be available to operating system, they would be available to the root, to the person or the program with the root privilege or root access. Okay, if there are some applications hidden installed in a computer program that they can provide the attacker some type of root access, those applications or programs, they are called stealthing rootkits. In fact, stealthing rootkits, they provide the attackers administrative access or root privileges to the system, which is of course something I think I would say ideal for the attackers. If I'm an attacker, what I would like more than root access. There is nothing more than root access. If I get root access for a computer system, that's what I need. And of course, I'm not gonna show my presence. I'm not gonna do anything that that makes it clear to the owner or to the operating system that I am here, I exist here, and I have the root access. So I prefer to stay hidden. That's why I say that for stealthing rootkits, the payload is staying hidden. So they prefer to stay hidden as long as possible in order to take advantage of the uh, privileges or access that they have and do whatever they want to do. Okay, now I'm gonna talk about the characteristics and classifications that we may see over different rootkits. Um, some of them are features like here, these two, and some of them are classifications. So I coded them this way. For example, you see here, I said A1 and A2. This means that this is a classification. We have a classification for rootkits. Rootkits might be persistent or might be memory-based. A persistent rootkit is a rootkit that stays on a system forever. It means that even if you boot or reboot your system, your computer system, you are not going to get rid of the rootkit. Why? Because the rootkit has stored some type of code or some type of program somewhere in the non-volatile memory of your computer. This might be, for example, the hard disk, or the boot sector of your hard disk, or whatever. But anytime that you reboot the system, the rootkit is going to be restarted with your operating system, and it takes again the same privileges. It accesses the same privileges as the previous time, and it has the privileges that your operating system has. So these are called persistent rootkits, and of course it is not that difficult to find these type of rootkits. You just need to try to boot in a different way, uh, uh, and then scan your non-volatile memory, for example, your hard disk. The way you can do this, for example, you have your computer, instead of booting from your normal root, for example, from your hard disk, you just insert a bootable CD or bootable flash, and you boot from that, and then you run the scanner program or antivirus program or rootkit program, and it shouldn't be difficult to detect, because there should be some code regarding this rootkit in the persistent memory, in the non-volatile memory in your hard disk, and of course you can find it and treat that. But of course, you need to boot from a different kind of booting device, not from your normal boot device, which is your hard disk. You should boot from a different thing. This, in contrast, we may have rootkits that they're memory based. Of course, when we say here memory here, we are talking about main memory, which refers to your, in fact, to the RAM you have in your computer. Some rootkits are in fact processes. There are some processes in the main memory. So we have the CPU, and next to CPU we have main memory, and a portion of these is kind of the code of the rootkit. The rootkit code is here, and of course it's a persistent code. It's a resident code. It is being executed like the operating system, and it has the same privileges that your operating system has that privileges. And of course, it is way more difficult to detect these type of rootkits, but one good thing about them is that they cannot survive the reboot. It means that as long as your computer is running, they are there and they access the privileges. But the moment you reboot your system, the moment you restart your computer, they are gonna go and they're not being there anymore. Of course, you may say that, okay, this would be a big shortcoming. Yeah, but those kind of attackers that develop this type of rootkits, they don't install it, they don't send it to normal computers. They send it to servers or computers that they're sure that they are not gonna be restarted or reboot every single day. Like, for example, our normal computers, they send it to servers and computers that they're supposed to be run 24/7. Okay, one feature, this is the first classification or category that I've just talked about it. And now I'm gonna give you I'm gonna talk about two features for our existing or now rootkits. Some of the rootkits are virtual machine based rootkits. What a virtual machine is, a virtual machine, for those of you that might not be familiar with the concept of virtual machine, a virtual machine is in fact a program that you install on your computer, and it makes a software or soft clone of your computer. And when I say clone, it means that everything is being cloned, everything is being copied, but into a software version. So this is your computer. You have CPU, memory, hard disk, IOs, blah blah. Through the VM virtual machine, you'll get another copy of this computer. And of course, you have control over it. For example, you have here, let's say, 2 GB of memory, of main memory. You can just send, let's say, 500 megabytes of that to your virtual memory. So in your virtual memory, you have, which is basically a program installed and run on the original physical computer. That program gives you a virtualized version or a cloned version or a software cloned version of your physical computer with up to 2 GB memory. Of course, you have access. You may limit that. You may say that, okay, in the virtualized or the cloned software version, I just want to have access up to 500 megabyte of memory. The good thing about virtual memory is that whatever you do in the uh, I'm sorry, virtual machine. If I said virtual memory, I meant to say virtual machine, because we also have the virtual memory. In the virtual machine, um, the good thing about virtual machine is whatever action you want to do in the virtual machine, it is being processed in the virtual machine, and eventually it's going to be issued to the actual physical machine. And this is, at the end of the day, this is a processor on the physical machine, which is supposed to run the program or instruction, even of the virtual machine. So there is a very big kind of like a gateway here, that everything from the virtual machine at the end of the day needs to be passed, needs to be transferred to the physical machine for ultimate processing or ultimate action. So uh, this gives us a very good level of control. We can bypass some of the instruction. We can, for example, monitor them. So, but these type of rootkits, they do it they use it for malicious purposes. They come, this is your physical machine. They install without letting the owner or the user knowing this. They install a very lightweight virtual machine, because one major problem with virtual machines is that the soft version or the cloned version are usually or often they're way slower than the physical machine. So it would be easy for the owner to detect that, okay, now I'm working on the virtual space, not on the physical space or physical environment. But they install a lightweight virtual machine, so they give you a virtualized or a clone of your computer, and everything the actual user is doing is being done at the virtual environment. And they, of course, the hacker sits here in between, and whatever you want to do, the hacker now can access over it, can modify it, can bypass some of them, and can, for example, intercept some of them. So this is a very good idea to develop the rootkits, so that you have, the hacker would have a very good and high level of access, uh, something similar to the operating system. So this is one feature that some of the rootkits use it. And of course, if a rootkit is a virtual machine-based rootkit, it needs to be implemented in the memory, because in order to move a physical computer, in order to transfer whatever a user has from the physical environment to the virtual environment, you're gonna need at least one boot. You have your you have your uh, the user's program and the user's data here. You want to transfer it here. At least one reboot is required. So that's why I say virtual machine-based rootkits. They should be, of course, uh, one, of course, they fall, of course, in the category of persistent rootkits. There is also another special type of rootkits, which are or feature for rootkits, which are called external mode rootkits. And this type of rootkits, it says they're not in the main memory or even in the external memory like hard disk. They're somewhere out of this main computer. They're, for example, in the BIOS space, in the RAM space, which is of course not easy to place the rootkit here, but for some computers, if they have vulnerabilities or exploits, that can be done. And if the rootkit is placed here, it can kind of work in parallel with the operating system, and it can even have access to the hardware, which makes them very more dangerous. But like I said, it's not easy for getting access to the, for example, BIOS or uh, kind of spaces in parallel to the our main physical computer. Okay, another classification for rootkits is the level they work, user mode or kernel mode. What I defined for the rootkits, that I said they have the privileged accesses and they can do whatever they want to do, uh, exactly similar to the accesses or privileges that the operating system has. They are in fact called kernel mode rootkits. In the kernel mode rootkit, all the system calls, operating system library functions that normally user programs, for example, you have your, I am a normal user and I've written a program to send some information to printer in order to get it printed. So I normally don't have access, or my code normally doesn't have access to IO or printer. What I do in my code, I call some functions which are called APIs, application program interfaces, and I can now get access to IOs or printers through APIs. So my code is not allowed to directly communicate with IOs because of the security reasons, but I can use, of course, the APIs that operating system provides me, and I can do now whatever I want to do through the APIs. In the kernel mode rootkits, the rootkit developer could have done all changes in a way that uh, it could he or she could have kind of rewritten or overwritten the APIs. For example, here is a normal program is being run here, and it at this point, here, the user program is supposed to call APIs or operating system subroutines, like for example, this one and this one. The code of this, for example, sys4, it has a code somewhere. It has a list of instructions somewhere written. We don't want to look at it. But whenever the user program wants to start something, wants to create a new process or a new thread, it calls this system call, and now this is the operating system that performs that, for example, sending data to printer. In the kernel mode rootkit, the hacker found way to override these functions. And you see, instead of calling, when the user calls this function or this API, this is the kind of hacked version. Now it jumps to a different subroutine, which is a hacked subroutine or tampered subroutine. This is the original one. Instead of jumping here and running this code, The user code, this is the user code. This is the user code, and here is the operating system API. Instead of calling the intended API, the user jumps to a different API, which is totally written differently by the hacker, and it may do whatever it wants to do. This is called kernel mode rootkit. We have another type, which is a slightly kind of low, it needs a slightly lower level of access at which the user, the hacker couldn't override or couldn't write a totally different API. Instead, what he or she was doing or is doing is that he just tries to compromise or tamper the results which are being returned by the API. So it means that, so this is a kernel level or kernel mode rootkit. In a user mode rootkit, what it's doing is that you as a user call this system call, performs something and returns you something. The user mode rootkit, they just change the return result. For example, here it returns, let's say 0 or 1, meaning that, okay, I have created the process successfully, or I couldn't. Now the rootkit only can change the result. It doesn't. It wouldn't be able to implement it totally differently. But what it has done is that it just changes the result. And of course, this is a kind of rootkit with lower level of accesses, not exactly similar. I'm talking about the user mode. The user mode rootkits, they have slightly lower accesses or privileges than what the operating system has. But still they have the capability to change something and to fool the user. Okay, now we are done with the payloads. We've talked about multiple of different payloads. We've talked about 4 different payloads, and now I'm going to talk about countermeasures. First of all, let's refresh your mind. What is a countermeasure? We said any mechanism, any architecture, any algorithm that we develop on a computer system in order to defeat any type of malicious activity or threat or attack, that is called a countermeasure. In fact, the countermeasure is the owner, is some actions that benefit the owner of the computer system from security standpoint. So it helps us to attain our integrity. It helps us to attain our, let's say, availability or our confidentiality. So we have introduced a couple of different cyber attacks, and now I'm going to talk about, again, some well-known and widely used countermeasures. The first countermeasure is antivirus, or this is of course a name. It doesn't mean that they're only targeting viruses, but we generally call them antivirus softwares. An antivirus software is a program that tries to detect and defeat viruses and worms and Trojan horses and maybe rootkits or backdoors or any of the malwares that we talked about. And of course, you know that they are very widely used, and almost every computer has some type of kind of, these days, any type of computer, they have some type of antivirus program. We can say that they are somehow intrusion detection systems. We will be talking about intrusion detection. Intrusion detection is a type of mechanism that you develop in a network environment, and that's something that tries to protect different clients or different computers in a network. For example, in ANT's network, we are all when we are on the campus, we are all under the ANT's domain. And when we want to get connected to somewhere, there are some firewalls or some computers that they try to detect and protect us. So this is an example of intrusion detection. If someone tries to attack one of the computers or one of the users in the ANT, he or she needs to pass through the firewall. But antiviruses, we can see them as an intrusion detection system which are being installed, which are running on the end computer. So we call them host-based. They're on the very end computer and try to protect that computer. So there are software programs which are being run on our computer and try to protect our security, our computer from kind of different type of malwares. Okay, I'm going to talk about different classes of antivirus software, and there are multiple generations of them. But I just want to start with this, that it was very easy to detect malwares or viruses. It used to be very easy because the malwares used to have a very simple code, and it was easy to detect that code. And having this said, for an antivirus or anti-malware, the antivirus just was supposed to search for that code and find it. But this is what we call it as a first generation of antivirus software. In the first generation, that they are working based on the signature, they find and they kind of develop a database or kind of dictionary of the signatures for different malwares, for the known malwares, and they just scan or search on the file that you have in your computer and try to find those signatures. Of course, it's very kind of easy to say that to detect their problems or shortcomings. You just or the antivirus system kind of effectiveness is limited to the dictionary or the signatures that they have had at the time. That's why if I'm not sure if you have used this type of antivirus on your computer. If you have used them, you remember that there were a process called signature update. You had to update your signature every day maybe, or every week or every month, in order to have the signature of the database signatures up to date, in order to be able to protect your computer against the most recent malwares. Okay, the second generation, they just try to kind of improve it. They said, okay, we look for the signatures, we keep the signature database in our antivirus software, and we try to find those signatures in the existing files in our computer in order to find matches, and in order to say, okay, hey, this is an infected program, and it should be cleaned, or it should be quarantined, whatever. But on top of that, we apply some heuristic rules as well. And we don't sit and just check the signatures. That's of course something that we should do, but that's not all that should be done. Other than that, for example, you remember we talked about the viruses or the worms that they encrypt themselves, and we said that the encryption helps them to stay hidden. It helps them to kind of not being detected by the operating system or by any antivirus. In these heuristic rules, one example is this: the second generation of antivirus that they use heuristic scanners or heuristic rules. They try to find the encryption portion of the code. If this is a virus or a worm code, there should be at some place some encryption routine that encrypt the code, because of course you at the end of the day you have some code and you want to encrypt it. One portion of this code should be related to the encryption. This part starts, and this is the main entrance of your malware, of your virus or worm or Trojan, and this encrypts the rest of the code. And after encryption, of course, you don't see it, you see something else, which is now encrypted and it doesn't match with the existing signatures. But that portion of encryption and decryption is still there. You have it. So they try to find the signature, the encryption portion of the malware. They're trying to find the cryptography key. And after finding the cryptography key, you can now decrypt the coded versions of the malware, and you can easier detect them. So you see, this is something that, of course, it doesn't apply to this just signature matching. You are doing some, you are in kind of deducting some conclusions. You are saying that, okay, this is a malware that it encrypts itself. So let's find the encryption's key, and let's try to decrypt the codes, and then I'm gonna apply signature matching. Or if you find some code that it's decrypting, is decrypted, and it's and you can it's encrypted and you can decrypt it using that key, most probably that code uh, should be malicious, because what what's the reason for a normal code to be encrypted? Another approach is in the second generation of antivirus is to just use integrity checking. Integrity checking, it means that they look at the integrity of system. It means that other than they basically they change their standpoint, the point of view. They don't look at the codes in the memory or in the main memory in order to find the malwares. They look at the user's file and product and let's say document, in order to see if they're safe or they're being compromised. If they find something, if they find some uh, programs or files from the user which are not, which are kind of which they have lost their integrity, means that they are not working anymore, or something happened to them, it means that there should be something, and now they go and try to find the malware, which is of course has some kind of shortcomings. You need to let something happen, and then you can go and detect it. The second generation of the antiviruses, on top of the first two approaches, they also kind of look at the behavior of the system, the whole system. Their resident program, their memory resident program, it means that this type of antiviruses, there's something similar to operating system, that they are being executed in parallel with the operating system, and they look at the system's behavior. And if they find something abnormal, if they found something which is not normal, which is not usual, that triggers some more kind of that triggers in then that, okay, something might be here suspicious. Now let's go and double check or triple check that. Yeah, and in the fourth generation of the malwares, we have it can be we see a combination of what we have mentioned in the previous generations. They also have uh, trap component. It means that, and access control capabilities. Access control capabilities means that what you see, some of the files or some of the documents in the computer are protected. Not every application is allowed to open some files. Like what you see in operating systems. For example, if I define two different users in my personal computer, either Windows or Mac, I can change the setting in a way that, okay, documents which are being generated, which are being created under user A, are no longer accessible in the when user B log in. So this is some type of access control at the software level. in order to protect some documents and some files from other users. So this might be applied to the processes as well. When a single user logs in, there might be multiple files, but not all of the files should be shared or should be available to all processes. Some of them should be protected from being accessed by some of the processes. This is called access control capability, which is we talk about ideas and the methods of access control. There are, of course, many ways to do that. I'm not talking about how we do it, but the fourth generation of antivirus system, they try to implement some access control. And also they have trap mechanisms. It means that they do something in order to detect malicious codes or malicious programs, if any. They try to show some kind of options to them, so that if there's any malicious code or malware, they try to attack, and then that's not a real vulnerability. That's a fake vulnerability in order to just trap the malware. Okay. Another countermeasure, the second countermeasure I'm going to talk about, is called sandbox analysis. Sandbox analysis, if you remember, we just talked about virtual machine and virtual environment. And I said that you have your physical computer with all of your resources, all of your hardware components plus operating system. You can run a program, you can install and run a program, that program called virtual machine, and it gives you a clone software copy of your actual computer. And everything on this clone computer can be, for example, the memory can be as big as what you have in the physical computer, but of course it can be even kind of less than that size. Everything in the virtualized environment, at the end of the day, for the ultimate run or execution, should be sent to the physical machine, or is being executed on the physical processor. Okay, this virtual machine idea, it means that you have an environment which is highly controlled. So the sandbox analysis, it says that we create a virtual machine, we create or we define a virtual machine copy of our original computer, and now we let the programs to be executed to be run here on this virtual machine environment. And of course, if there is any vulnerability, any potential malware, they try to start, because malware doesn't realize malware is not trying to detect if this is a virtual environment or physical environment. It just thinks that the malware will be treating in a way that this is the actual computer, and if there is any malware, the malware starts propagation and then it starts running or executing the payload part. So if there is any malware, the malware shows itself here in the virtual environment, but in the virtual environment, everything is under control. We don't let the actual, we don't let the malware to run the actual code. We just, after the malware tries to do that, tries to, for example, let's say the malware tries to delete a file. The malware deletes the file from the virtual environment. The delete command will be sent to the physical environment for commitment for actual run. But here we are analyzing the system, and we said, okay, this delete is not something that should have happened. So we just ignore it, or let's say we bypass it, we refuse it, and now the malware is somehow detected because it has shown its payload, and we can detect the malware, but we are safe. The actual file wasn't, sorry, give me a second. The actual file wasn't deleted. So this way we can find the potential malwares or malicious codes that we have in our computer hidden. And of course, there is a big question here, and the question is how long the virtual environment should be run. If I run the virtual environment for 1 hour, is that enough? If I run it for 1 day, is that enough? And there is, of course, no clear answer to this question. The longer you run, the more you can say, okay, there is no malware, or this system is clean, or higher chance for you to detect some malwares if you have any on your computer. Number 3 countermeasure is called host-based behavior blocking, which is similar to the fourth generation of antivirus systems that I just talked about them. Here you have a program, or let's say software, that tries to dynamically analyze the behavior of your computer. It can be integrated as a part of your operating system on the host computer, and it monitors the behavior of the system in order to find any malicious activity or any payload at the real time or at the runtime. Of course, this might be a part of an antivirus program, but you might have this as a separate thing. It means that you are just looking at the behavior of your system. You don't have any signature based, you don't have any rule based scanning. You just look at the behavior of your system at the runtime. So that's why you see it here as a separate countermeasure. If you just have the behavior monitoring part in your computer, that's itself a countermeasure. If you have a fourth generation antivirus, that's also which has this part in it, this is somehow a subset of the antivirus generation 4. This also that's why you see them. I put them as a 2 different countermeasures, because some systems, they don't install, they don't have an antivirus, but they have a host-based behavior monitoring and blocking. And of course, if you only have the behavior monitoring, you're always subject to this question, that how the behavior monitoring system is supposed to protect me before the malicious activity happen. Of course, my system is under run and everything is normal, no kind of unauthorized file access, no unauthorized file delete. Eventually something's happened, one of my files or some of my files are being deleted by an unauthorized program. This is of course an anomaly that the dynamic behavior monitoring system detects that, but the files are now gone. It means that this type of countermeasures, if they are not being supported by other things like what we mentioned in antivirus generation 4, they can end up losing the information or the data, or losing access to some of the resources in our system. So what I'm saying is basically this is a countermeasure by itself, but it has a limitation, and mostly that's why people use it as a part of antivirus. It should be supported by some signature-based and rule-based monitoring as well, in order to detect most of the malwares before they get activated, before they triggered and the payload gets started. Okay, what I'm now going to talk about is denial of service attacks. This is, of course, a different type of attack that we have seen in computer systems, and it's different than malwares. And the main target of denial of service attack or DOS attacks is the availability. They try to compromise the availability of the system in a way that some of the services or some of the resources of our computer is no longer available. So they are mainly target availability. There is no confidentiality, integrity compromise here, in contrast to what we have seen for the malwares that we talked about them. They were mostly talking about integrity loss or confidentiality loss, but here we are talking about availability loss. This is a definition of DOS attack or denial of service per National Institute of Standard and Technology. They said an action that prevents or impairs the authorized use of networks, systems, or applications by exhausting resources such as central processing unit, memory, bandwidth, and disk, and etc. Okay, what it's basically talking about, it says that you are not getting access to uh, the services or resources that you are supposed to. It means that the services or resources that you are supposed to get to have them, they are no longer available to you. It might be through, it might be implemented through compromising, for example, uh, network bandwidth. We will be talking about bandwidth violation, and we'll see that some of them, they try to occupy the bandwidth. So here is the attacker, here is the victim machine, and try to use all the bandwidth that you have. It means that you have everything is ready. The only thing which is not available to you is the bandwidth. So you cannot send and receive information. That's it. The, the resources or some of the, let's say, websites that were available to you are no longer available to you. So they have fully used or exhaust the, let's say, the bandwidth, and that's why you don't see that. But the bandwidth is one example. It might be through exhausting the memory or the processing unit, CPU, whatever. So we can, in a short, define the denial of service attacks: any attack that try to compromise the availability of our computer system and the services or resources which are supposed to be available to us, they are no longer available. And because of this definition, because of the nature, they're mostly remote. What it means is that if you have a computer, if I send you a Trojan or a worm or a virus that it tries to, let's say, takes the CPU and use it, let's say 100% of time of the CPU, of course, it's going to be very easy for the operating system to detect who is kind of consuming the CPU 100%. And it's going to be very easy to kill that process. Or if I send you a Trojan that tries to, for example, occupy the main memory, or just make some fake files in order to fully occupy your disk, again, it's going to be very easy for you to detect it and to protect it, to protect your computer. But if I do that over the network, if I do something from a remote computer, you may even detect it, but it's not easy for you to prevent against. So that's why we see most of the denial of service attacks that are being implemented and designed for remote attack. Okay, let's talk about the resources that we said might be compromised with a DOS attack. The first thing is network bandwidth, which is basically the most important one. Here, this figure shows, let's say you are the actual user, we are the legit users, and there are some servers over the internet, let's say, for example, Google or Yahoo, whatever, and we are being connected to them through some links, through some connections. Of course, you are connected to your first level router, and through that to some other routers. You go over the internet, your information goes over the internet, and eventually it reaches to the Google server. If some attacker come, and attackers just try to use the bandwidth, what would happen is you are still connected physically, but your packets that you are sending to this server are being dropped because the whole bandwidth or the whole capacity of these links, or some of the links, not even all of them, some of the links are occupied or 100% used by the attacker. So your packets are being dropped and you cannot talk to the server. That's that's the way that they do, they attack the bandwidth. They fully use the network bandwidth, and that way they can drop some of the legit packets, and we are no longer having the access to the server. And we are getting, for example, timeout error. It says that, okay, timed out and your packet couldn't reach the server. To us, it means that we are not connected. Although everything physically is kind of correct, and physically everything is connected, but we don't receive, or we don't get the services that we were supposed to. Yep, and this is basically coming from one fact that most of time our connection to our ISPs is in terms of bandwidth is not the same as the bandwidth that we see here. This bandwidth, it might be smaller than the bandwidth that we get here. So we can pass this link, but the final links which are shared between different users or different clients over the internet, they might have lower bandwidth. And if someone uses 100% of that, or a good percentage of that, let's say 90% of that, we would have a hard time getting access to that 10%. DOS, or denial of service, might apply on system resources as well. For example, like I said, the CPU time or the memory might be compromised. Of course, as I explained, if someone attacks to the CPU time or memory of a computer from a local computer, I mean, if you are on the same computer and the attacking malware or the source of attack is also on the same computer, it would be easy to detect and to just kill them. Because after the memory is full, you look what's this process that is using the whole main memory I have on my computer. You can just terminate that. Even we as a user, we can manually terminate that. So it shouldn't be very difficult. That's why even sometimes system resources which are being attacked in a DOS, they are not being attacked from the local computer. They are being attacked over the network. Or application. You have applications which again comes from the network, and those applications, they try to send huge number of valid requests. Huge number of valid. The request itself is valid, but they send you huge number. I'll show you one of these to you. They send you a huge number of those requests, and the system now is overwhelmed with a huge number of valid requests, which the system is supposed to respond them. So again, the system probably will not be able to respond all of them. So if there are some legit requests among the requests that they are coming, most probably that will not be receiving any response, or will not be receiving the services by the time that he or she is supposed to. These are called application resources that might be compromised or might go out of service by the DOS attack. Okay, now let's see some of the real DOS attacks. I'm going to talk about some of the network related DOS attacks, and I start with the attack which is called ping flooding. Before getting into that, I need to say what is a ping command and ICMP protocol. I just very high level and in a very abstract way I'll be talking about it, because we are not going to go to details of these kind of protocols or packets. We just want to see their kind of objective. Let's use this ICMP as the attendance code for today, with the same kind of spelling, ICMP, all uppercase. Okay, the ping command, which is a part of the ICMP protocol, it is a kind of classical network utility, um, which is being used to measure the time, turnaround time or time to return. You send a ping command to, for example, some server. You are a client. You send it to any server you like, and one packet goes here and one packet returns, and your computer measures the time from the request was issued until the time that the response was received, and that's called round trip time, which shows us how the network is fast, or how our connection is fast toward that specific server or not. Okay, how the user use the ping for DOS attack is through flooding some ping packets. This is the attacker. They just initiate thousands of or hundreds of ping packets toward the actual server. And the server, of course, needs to respond each one separately, because this is a part of the ping packet. This is a part of the ICMP protocol. And that that consumes a good portion of the bandwidth, the network bandwidth of the server. And if there is any legit client that tries to send some request, some other type of request, it might be HTTP, it might be TCP, whatever, to that server, that packet or that request most probably will be refused, will be dropped by the server, because server is now busy with some kind of unimportant, with some junk flooded ping packets. So the aim is to overwhelm the network bandwidth. Look here, we are talking about this image is an abstracted image. It means that let me clear. Yeah. It means that here is the attacker. Maybe this might be also better. And here we have multiple routers. And let's say this is a server. This is the attacker, this is a server, and here is another client, a legit client. This legit client is also trying to get connected to this server, but this specific link is now overwhelmed. 100% of its bandwidth is being used because of the ping packets which are being flooded from the attacker. And the packets that come from the legit client is being dropped by this router. This is a router, and this router drops the packet because it cannot forward the packet over this link. So the link here, it doesn't serve legit packets, because many fake ping packets are being transferred from some attacker. So this is a ping flooding DOS attack. And of course, it is not difficult to detect who is attacking. It is not difficult to detect the attacker, because every ping packet that the server receives, it has the IP address or the address of the sender, which is actually the address of the attacker. So it can be easily detected. The server can easily detect and block it. And after detecting that, even some legal actions may happen, because you can now kind of sue the person who is the owner of this server and use this system, and use this system to attack you. Another from the attacker's point of view, I'm talking another limitation of a ping flood is that, which is actually can be used as some type of defeat mechanism, is that the server can respond. Of course, if the ping packet comes, the server is supposed to reply that ping packet, because this is a part of this ping ICMP ping protocol. The server is supposed to reply, but the server, when replies, can also send a ping from the server to the to the attacker client. And this way, the attacker itself is being attacked. And most probably the attacker will have to reduce the traffic, or reduce the will end up reducing the number of pings that he's sending, because he now is getting more busy because he receives many ping packets as well. So these are the shortcoming of this kind of simple traditional ping flooding attack. And of course, the network performance is also being affected noticeably, and everyone can realize that who is the attacker and which routers are involved, and it can be easily kind of treated. That's why a second version of that is called spoofed address. It is a ping flooding with spoofed address. Spoofed address means that this attacker now is sending the, let me go back to this slide here. Oh, sorry. The attacker is sending ping packets, but it tampers the IP address, and every ping packet, it has a fake or an unreal IP address. So, for example, this one has IP 1.1.1.1. The second one has 2.2.2.2. For example, I'm just giving numbers, and so on. And that way, once this server, which is being attacked, it receives the ping packet. Every ping packet from the target, from the server's point of view, every ping packet is coming from a different source. Of course, they're all coming from the attacker, but the attacker just changes its IP. It doesn't let this original or real IP to be appeared on the packets. It just changes them to something fake, something random. You may say how this is possible. Yeah, this is possible through some socket programming, or socket interface is a kind of traditional approach that you can get access to the contents of HTTP or TCP or IP or different types of protocols of over the internet, and you can modify the contents of packet before having them over the network. It is basically a something that operating system allows you to modify the contents before they go out of being injected to the network. Basically, it is a way that the operating system gives the user to communicate with the network adapter directly. So here is the user program, here is the operating system, and here is the network adapter. The new user uses operating system to send data to the network, and through that to the network. But there are some ways that you can directly change the data, and one portion of that is the IP address. You can change it, and that way the victim or the server receives too many ping packets or ping requests and replies them to to random kind of clients, because every ping packet which is being produced by the attacker, it has a random IP address. So this is another version which is not easy to detect it from the server point of view, because the server now is not able to understand who is the actual initiator or senders of all of these. Initially, ISPs are supposed to monitor their outgoing traffic to match the packet with their packet's IP address with their real IP address. It means that I am an attacker, I'm getting my internet from some ISP, and the ISP is internet service provider is supposed to check the IP addresses on the packets with my real IP address. And if they are not matching, the packet should be blocked, shouldn't be forwarded to the network, to the internet. But most of the ISPs, they just don't do this part, because they say, okay, this is not my responsibility, and it takes my resources. Of course, they need to run some application to do that, and they don't want to do it. They just forward whatever packet they receive, and that's why the DOS attacks are still doable. I'm sorry. I know that our video is getting slightly longer, but but it's not gonna be too long. I just want to finish. We have 2 more slides. I just want to finish this topic because you need to. We need to get it done before the exam. It might be another 5 minutes or maximum 10 minutes. Okay, the second type of DOS attacks that I'm gonna introduce, it is called sync spoofing, which is this sync is a part of the TCP packets or TCP protocols. Here you see how a TCP connection is being established. The client or the requester sends a sync packet, which is a packet or the first packet of the TCP connection or TCP protocol. And then server lists the information which is being received from the client on a table, says that, okay, this person with this ID, with this port has requested at this time. And then sends acknowledge or sync ACK. And then after that, in the third kind of phase, the client sends the ACK and then connection is being established. And now the client and the server can talk and communicate, can transfer data. And that's how, for example, we receive the data from web servers, from google.com or from whatever ncat.edu. That's how our connection is being established. Okay, in the TCP sync flooding, the attacker is not sending the ping command. Instead, he or she or the system is sending too many sync packets. That's just it. It sends sync packet. Of course, the sync packets, they use the bandwidth of the link, and some legit users, some legit clients, their packet might be dropped out, might be thrown out. But on top of that, there is another problem that will happen. And that problem relates to this table that I just talked about. As I said, there is a table which is called connection table. And it every time that a new client sends a sync packet, which is the first step of the TCP protocol, one row will be added to that table. The problem is this table is not supposed to have infinite length. For example, they normally say, okay, this is ncat.com. We normally have 10,000 students, let's suppose, and we are saying that no more than 20% of them wants to get connected at the time. So we need this table to have the length of maximum 2,000 lines, not more. Anything about 2,000, we drop it because normally we don't get that many concurrent users at the time. So they define this table to have the maximum length of 2,000 rows. If I'm an attacker, I just need to send at least 2,000 sync packets, and that way I can use the whole connection table. And the whole connection table is being used by fake sync packets. And if a legit request comes and there is no more room in this table, and the server says that, okay, my table is full, so let's get this new request dropped. And that way the legit users are no longer available to get connected to the server. This is another type of DOS, which is called TCP sync flooding. And of course, again, the the attacker, what he or she will be doing, this is a basic thing. He doesn't send all of them with its own real IP. The attacker changes its own IP. So the server thinks that whatever server sees is the server kind of assumes that multiple requests are coming from different users all over the world with different IPs, but this is not basically true. These are all coming from the same source, which is the attacker, but the attacker is changing its IP address. So to kind of deceive the server. We just talked about two of them, ICMP or ping flood, TCP sync flood, that of course you see that they can they can consume the bandwidth between the clients and the server, or they can use the connection table, or in the, for example, the last one, UDP, that I'm not going to go through the detail, they use the memory limitations in receiving and sending files, because the UDP packets are support connection. This is also the name of a protocol. We have UDP protocol that that UDP packets are being produced based on this protocol. And in a UDP flood DOS attack, the attacker sends too many UDP packets with so many data in them, so that the buffer that the server has will be full, and there is no more room for new UDP connections or UDP packets, and the packets that are coming from the legit clients or users, they're being dropped. And now I'm going to talk about distributed denial of service. These are what we have talked about. We've talked about three different types of DOS, which are all being done by a single attacker person. And eventually, we have only one computer that is attacking us. Although the server may not realize that, or may assume that their data or the requests are coming from different sources, but eventually, or in reality, they are coming from one attacker attacking computer. That's called DOS. But in distributed DOS, the story is different. We have a bot master, we have a person that has sent so many bots. We've talked about bot malwares that has sent so many bots, and the bots now compromise many computers. There are different computers which are physically located over different places on the internet or over the world. And now their computers are infected by Trojans or by bots or by spams, whatever. And now the bot master or the person or the server that kind of coordinates all of these bots, it implements some DOS attack, might be any of those DOS attacks, through real computers which are being placed at different at different places over the internet. And it's even make it more difficult. This is called distributed denial of service or distributed DOS. Of course, there might be a simple architecture like this that the bot master controls the bots, or it might be even more complicated. This is the attacker or the bot master. The attacker communicates with some first level computers, which are here. And each of these first level bot masters, they are communicating with multiple compromised computer that they have bots on them. And then once this guy fires the order, issues the order, it goes to the second level kind of managers. Each manager, I mean the bot managers, each bot manager sends it to the actual computers which are being compromised. And here we have the bots. Actually, the actual bot is here, the actual bot is here, and so on here. And now each of these compromised computers perform the actual attack over the victim, over the server or destination. That might be any of the mentioned flooding attacks. So again, it would be way more difficult to detect and to protect against this. I think this is the final thing that I wanted to talk about, and we are good to wrap up here.